recently very popular programming language concept called algebraic effects and handlers. Yes?
The microphone is not on.
Hello?
Yes, sir.
Okay, maybe I just need to speak louder. Right, so the lectures will be about algebraic effects and effect handlers, and my goal after these 3 lectures is for you to get to know what are algebraic effects and what are effect handlers and how to program with them. So first, a few acknowledgements. I took some of the inspirations from Gordon Plotkin's lectures on algebraic effects at an international meeting in 2019, and I reused some of the examples from Sam Vigili's lecture also at OPLSS 2022 on effect handler-oriented programming, but I hope to bring my own perspectives in my lectures. And I may or may not have time to talk about some of my recent work on algebraic effect handlers, but here are the list of collaborators that I have worked together with on topics related to this. All right, let's get started. So I am a big fan of functional programming. I like pure programs. But the reality is, right, there are side effects everywhere. Like maybe you want to read from the user input, maybe you want to print something to the screen, you want to read from a file, you want to write to a file, maybe your program will throw an exception, it will use some mutable status, or maybe your program messed up with the control flow, there's concurrency and backtracking and other kinds of non-determinism. And what's worse about this is in lots of programming languages, right, effects are often ad hoc and hard-coded, in the sense that they are always implemented separately and you cannot really change the behavior of them. And maybe some of them will even interact in a very bogus way that triggers some very complicated bugs. So in this lecture, I want to convince you that algebraic effects, they provide composable and structured control flow abstraction that allow us to define and use effects in a more flexible way. And algebraic effect and effect handlers are relatively new concepts in programming language community, where algebraic effects are come up with by Gordon Plotkin and John Power in 2001 with this forecast paper, and effect handlers come much later in this ESOP paper in 2009. So basically, they first come up with the semantic foundation for algebraic effects, as we will see are basically effects that satisfy certain algebraic properties that we will talk about. And effect handlers, they are later more like destructors of effects, if you consider algebraic effects as constructors for effectful computations. And algebraic effects recently have a growing interest in academia, and they are getting into more mainstream languages, right, like OCaml, and they use it to implement asynchronous I/O in order to express highly scalable concurrent applications, and it has been since then merged into the main OCaml compiler since OCaml 5. And there are work on implementing effect handlers as a library for C++ languages as a way to provide high-level interface for computational effects. And they use it to implement cooperative lightweight threads, actors, generators, lots of examples in the paper. And more recently, people are trying to implement effect handlers for WebAssembly to implement a non-local control flow. But it's still work in progress, and they have a prototype implementation in Western time. And just last year, there is another piece of work on effect handlers for C. And it's not only about academia, because there is a lot of usage of effect handlers in industry as well. So here I gave 3 examples on the slide, where semantics is a code analysis service at GitHub implemented in Haskell that we will get back to later. And React is a JavaScript library for building user interfaces. It's developed at Meta, and they use effect handlers to design hooks that allow developers to reuse stateful logic. And the Pyro is a Python library for probabilistic programming by Uber, and it has a library of composable effect handlers for creating new interface algorithms. And specifically about the semantics code service developed at GitHub, people at GitHub published a paper in 2022 at SFP, where they talked about lots of the programming paradigms used in implementing semantics. And that includes, for example, generalized LR parsing for pass the source code for a diverse set of programming languages, and they use data type a la carte for representing language syntax, and they use lots of recursion schemes for generating and manipulating syntax trees. But specifically, they used effect handlers a lot. And they used effect handlers to control the state of data, or how you deal with data. So to directly quote from the paper, they say, well, an example of the utility and flexibility of algebraic effects is an effect we developed to extract telemetry data from our production Haskell systems. In a production context, we wanted this data to be uploaded to an aggregator. In a development context, we wanted to see them reported to the command line. And when running automated tests, we wanted to discard them entirely. And effect handlers allow you to very easily give different interpretations of effects for operations under different contexts.
Why couldn't you use monads for these things?
Very good question. I may or may not have a slide for that. But an intuitive answer is algebraic effects are more modular, but monads are more expressive. If you care about modularity, then you should use algebraic effects. All right, so if you want to play with algebraic effects and effect handlers a little bit, there is a set of research programming languages that you can program in effect handlers in, and they are relatively well developed in the sense that they come up with documents and examples and tutorials as well. So you can try out these languages and try out their tutorials and see how much you like programming in effect handlers. And with that, let's talk about what algebraic effects actually are, right? I talked a lot about they are useful and people are using them, people are developing them, but what actually are algebraic effects? So algebraic effects 101. I will start with a question. So we say a lot, right? Like we have a program that may come up with some effect for computations. Maybe it will throw an exception, maybe it will have concurrency, maybe it will read or write to a file. But the first question is, how do effects even arise, right? How do we construct them in a programming language? Yes?
Calls to the operating system.
Calls to the operating system. Other answers? Yes?
Raising an error.
Raising an error. Yeah, there is one in the back.
Interaction with states.
Interact with states. Listen.
Writing to a buffer.
Writing to a buffer.
Writing to memory.
Writing to memory. Yes?
Oh, that's okay.
Something recursively.
And like
Not decreasing, like non-termination. All right, so when we say operations that we want to write to a memory, or we want to call operating systems, or we want to raise an exception, the first thing that we need is a set of operations, right? We are able to write in your program. Maybe you use this operation to write to a memory, maybe use this operation to call operating systems, or use this operation to interact with stateful resources. So you always need to come up with some of the operations that you would provide, for example, to the user. And maybe there are some properties that you would expect those operations to satisfy as well, right? Maybe if you read from a memory twice, and in the meantime nothing changes that piece of memory, you would expect to get the same content back. So what is an algebraic effect? At a high level, an algebraic effect is given by two things. First, a set of operations. That you can consider them as effect constructors, that you have to use these operations in order to occur effectful computations. And they come with signatures that we will talk about shortly. And there is a set of axioms or equations or properties that we would expect this operation to satisfy. And the best way to demonstrate this is with an example. So in this case, we have a Boolean location. a Boolean location, and it has three operations. We can put a true value, so I call it put t, or we can put a false value, I call it put f, to that location, or we can get back a value that is stored in that location. And these three operations, they have signatures. So put t and put f, their signature are both 1. And sometimes people call them arithmetics as well. And the signature for get is 2. So how to read this signature? You can read this put b, so I sometimes just write b as true or false. Put b as an operation that takes a single computation, in this case m. And it says, I'm going to put b into that location, and then I'm going to continue with this computation m. And get, because its arithmetic or its signature says it's 2, so it takes 2 computations. And get says, I'm trying to access the value that is stored in that Boolean location. And if that value is true, I'm going to continue running m, because m is a computation, or otherwise I'm going to run m, which is probably a different operation, different computation. Yes?
Is m generally like a continuation, like a lambda that will be called after put b, or is it more like a value that put b is going to return?
Very good question. In this setting, it's generally a computation. It doesn't have to be a lambda. It's not waiting for something. It's just a computation that runs by itself. And we'll see some examples written in this language. And given this set of signatures, right, we would expect some of the axioms or properties or equations that these operations would satisfy. And these are the 5 axioms for this operation. So let's go through them. So the first equation, the first equation says, if you try to get the value, and if the value is true, let's run m. If the value is false, let's run m. Now it's equivalent as if you just run m, right? Because the value doesn't matter. And there are 4 other axioms, and sometimes people call them get, put, get, put, and put, get, because it enumerates all the possibilities, right? And this get axiom says that if you get the value from that memory, and if it's true, then let's try to get the value again. And if it's true, let's run m, otherwise let's run m prime. And similarly, if the value is false, then let's try to get the value again. And if it's true, then let's run m. Then if it's false, let's run m prime. And as you can see, if you run these 2 operations immediately after each other, right, you would expect that nothing can actually change the content from that location. So the first time the get gets true, then the second time the get should also give you back true. So that means in the first case, you will for sure definitely get m out of it if the value stored in there is true. So we can directly reduce this whole get m prime to m. And similarly, if the value is false, right, we know that for sure this second get is going to get back m prime. So we can also reduce it to m prime. So this whole computation that you actually run get twice, it would be equivalent if you just get the get once and then you run the computation, depends on the value. So, and this also answers your question that this is direct computation. Put is similar to some degree, but it says like if you try to put a value b, like let b be true, true or false, and then you try to put another value b prime again, and then you run this computation m. Of course, the second put is going to override the first put. So afterwards, you will for sure get b prime in that location. So let's directly put b prime in that location and run computation m. And then this get put says, well, if you try to get the value, and in the case it's true, you are going to put back true, and then run m. And if it's false, you are going to put back false, and then run m. And of course, you know that if it's true, then putting other true will not change its value. And if it's false, then putting other false will not change its value. So it's equivalent to if you directly get the content and run m if it's true, and run n if it's false. Yes.
So the axioms that you are talking about are the result of your computational definition at all. So my question is that which one precedes the other one? I mean, you write the axioms for the effects, and then that is according to some computational definition that you have in your mind, or do you write the computational definition and then you derive the axioms from?
Very good question. So when you write this effect, the signature, and the axiom, you are not generally thinking about how the axiom are derived from the computation. Rather, you are thinking that however these operations they are going to be implemented, they should respect this axiom. Like if you actually have a computation that controls how get and set are implemented.
So no, what I'm saying is that what is the main definition? The definition is that get gets a Boolean value and continues with m if true and n other bars, or get is a function that acts according to the axiom. Which one is the main? Which one is the basic definition?
What's the second one you mentioned?
The second one is get is just some abstract function that fits into the axiom.
Yes, exactly. So consider get as an abstract thing. So this, like how to read them, is basically trying to build an equation. That you can ignore that. So the effect only comes with the signatures and the set of axioms that should be respected.
Oh, okay. So the computational definition that we talked about is our own like manifestation of the axiom.
Exactly. Yes, and you can actually implement it differently, as we will see. Yes.
So what I'm wondering is that in the end you probably want to put different effects together, and these actions, they don't really tell you like how this would interact with ambient effects, right? So what if I were to have this state effect, I were to set it, I were to do some other effect, maybe set another state and throw an exception and then read the state again. Like the actions you don't tell you that you get back to the state you set, so then what?
Right, that's a very good question. So these axioms are about these operations themselves. So how two different sets of operations that interact and what kind of axiom would you expect from them would be a separate question.
So they can interact under this framework.
They will interact with other effects as
Okay.
well.
So I guess as a tag on to that question, what is the type here of n and n?
So in this case, it's you can consider it as an abstract kind of computation.
Okay.
So we are not talking about types yet. So there's no types, but itself, for example, can be another get and put, or can be a value, for example, if you just return a value. It can also be, if you actually in a lambda calculus, then it can actually be other applications that just runs.
But if I wanted effects to be independent, do I have to add more axioms? Is that
No, you would only expect this set of axioms to be respected by get and set. So it doesn't tell you what happens if you have other effects, because this effect doesn't care about other effects in this case.
right?
Yes?
This may be a difficult question to answer, but I'm going to try anyway. Is there a formal definition of what is not an effect, or I should say a formal definition of purity?
Definition of what is an effect?
What is not an effect?
What is not an effect?
What is essentially pure?
What is essentially pure?
Like, is there a formal definition of that in your experience with these papers and so on?
I think it depends a lot on your context. Like, for example, if you are talking about monads, then you will be saying, there's it's just the identity monad, or there's no monad that the program just runs. And in this case, it will be like a computation that has no operations. But it depends a lot on your definition and context. Yes.
Is there anything that prevents us from introducing inconsistent axioms?
You can introduce inconsistent axioms, but you will make the equational theory inconsistent. So a point that we will briefly get back to later. Yes?
Wouldn't you want to split the top right axiom into two, where you can either sort of remove one put or remove the other put, not necessarily that there needs to be two puts?
Can you repeat the question?
So in the top right, you have like get and put true, put false.
Mm-hmm.
Wouldn't you want to say like get put true m and then n, and then say like that is equal to get mn? That you sort of don't need the put false in order to get rid of the put true.
You're saying we don't need this put false. in order to get this.
Hmm.
Uh,
Or
and-
that if n were instead, like if put f n were abstracted.
Mhm. Like, and then you would always have that hold, yes. I'm pretty sure you can derive that from this set of axioms.
But wouldn't that be more expressive? That because if I say get put true m and then an n that we don't know anything about.
Right. If you can derive that, then it's not more expressive. Because it's the same thing that we can express using the set of axioms. And I'm pretty sure you would be able to. Okay. And now I gave you this definition of algebraic fact. Well, it's not complete yet, but we will see more examples later on. So now, let's just say an algebraic fact is given by the set of operations and then the set of axioms. And with just this set of operations, we can already start trying to interpret them. We can try to interpret this set of operations according to what we imagine these operations will be doing. So you can consider this as the denotational semantics, or sometimes people call modalic semantics of the set of operations. So this is not yet effect handlers, because effect handlers will give you the power to give semantics to operations yourselves. But let's now consider that how we would interpret these operations and the set of axioms according to these interpretations. So let's say we are going to interpret this set of operations according to the standard definition of state monad. And the standard definition of the state monad is it takes this type X and then it says I'm going to convert the whole thing into a function. And then that function receives the Boolean value that is currently stored in the memory and is going to return a tuple that gives you back the original type as well as the current state that is stored in the memory. So for example, well, let's say now we only have constants and operations in this language. So let's try to interpret constants and this set, get and put operations according to this standard state monad. So what will happen when the thing is a constant, right? It's true or false. We are going to convert it into a function. And this function says that I take the current Boolean value stored in the location, so it's the lambda over s, and then it returns a tuple. Tuple of the original constant, and then the thing that is stored in the memory, because nothing changed yet. And if you try to get the value and then run m if it's true, run m if it's false, then you also convert it to a function that, again, takes the current value stored in the memory, and then you see whether this value is true or false. And if it's true, then you are going to, of course, interpret this m as well. And after your interpretation, right, m is going to become a function that takes the current value. So you are going to pass this current value to the interpretation of m. Or otherwise, you would interpret this m and also pass the current state value to it. And in both cases, these two cases, they don't change the value that is stored in the memory. But if it's a put, right, it's with the put b and then says, let's run this computation m, then you convert it to the function that takes the current content stored in the location, but you don't care about it because you are going to update it. And you are going to update it to b. So you pass b to whatever this computation m, the interpretation of this computation m. But you know that this interpretation of this computation m is going to become a function that takes the current state. And the current state has been updated to b by this put. Okay. And now this gives one possible interpretations of the set of the operations we talked about, right? But on the previous slides, we also have a set of axioms we talked about. So what's the relation between the set of axioms and the interpretation we have here? We say that an interpretation is sound and complete with respect to the equation if we can prove the equivalence between these two equivalence definitions. So if M is equivalent to M, which is something you can derive using the axiom, if this judgment is exactly the same as if I can see whether the interpretation of M is equivalent to the interpretation of M under this particular interpretation. And in this case, you can actually prove that it is sound and complete. So we will just consider one specific example as one example of how we can do this derivation. So on the previous slide, we have this axiom, which is put get. And put get says, if let's put t to the memory, and then let's try to get the value. If it's true, let's run empty. If it's false, let's run m false. But in this case, since you just put it, you will get exactly the value put in the memory location. So it's equivalent to just put t and then run one of those computations. It's either mt or m false, depends on. I think in this case I just put true there, just as a very specific example. So then in this case you will just run this mt. And now this is the axiom that we want, right, on the previous slide. And you can show that this interpretation does respect this axiom. So how to show that? Well, let's just write down the interpretation of the thing on the left-hand side, and then we can write down the interpretation of the thing on the right-hand side, and to see whether they're actually equivalent. So the interpretation for the thing on the left-hand side, let's do it step by step. Well, it is a put get, so we first see put, right? And then we know the interpretation of put is going to create a function, and then it's going to interpret whatever this computation is, and pass the value you are putting into the location to this computation. So in this case, we are going to pass this t to this interpretation of get. And we also know how to interpret get. So in this case, get will become a function that takes the current state, and it has the if then else expression that says if s is true, then let's interpret mt and pass the state s. Otherwise, let's interpret mf and pass the state s. And now we have this lambda that is immediately applied to the current state, which is t. So let's reduce it. And let's reduce it so it becomes like this. So we still have a function lambda s. But this s, this particular s, has been substituted by this t as an argument. So it becomes if t, let's run this with t, else let's run this with t. And you know that because it's already true, so we are going to pick the first branch. So this whole thing becomes lambda s, the interpretation of mt passed with t. And you can do the same for the thing on the right. Right? We know exactly how to interpret this put t and mt, which will become a function like this. And now you can see that these two functions are exactly the same. Yes?
How do you go in the other direction?
That would be much trickier. You will have to do induction. This all make sense? Yes?
Kind of except for where t comes from generally. I mean, I guess it's like we're defining like the denotation of semantics of these things. We get like functions that we need to like apply something to them. I guess here t is coming from like the thing we're trying to assign. Is that like kind of how it works? I don't know. I'm just trying to like generalize this a little bit, but maybe we'll just get there.
So the question is, where does t come from?
Yeah.
I think in this particular case, we assumed some constants in this language, and then they map to, in the domain, to booleans in the result. So you have true and false, at least in the semantics domain, that you can do the if then else expression on.
So in maybe more real-world examples where you have like a more complicated notational domain, you have lots of different effects, do you generally expect this to hold the implication from right, so that's this completeness?
But even you have more complicated effects, you would still expect this axiom to hold, right? Because it only talks about get and put, and it's abstract over this MT and F.
But I'm just wondering if it's kind of related to the other question I asked. Like if you have other effects and they some of them interact and some of them don't, do you generally expect this to be complete? That like I can only derive things that are proven by the action.
Right. So you would generally, if you care about equational reasoning and you care about those kind of equations, you would expect your program to respect them all the time. But in practice, it's also useful to have interpretations that does not respect the axioms, but people use it a lot anyways. And we will see one example, and actually 2 examples. Yes?
So could you regard this as compiling an imperative language into a functional language?
You can interpret it this way, yes. But it's more like we give semantics to operations because the operations are left abstract if you don't give them any semantics. Okay. Some exercise that you may want to do, which is first, you can show that other equations hold as well. And second, which is slightly more intriguing, is you can actually show the get-get equation is redundant in the sense that you can derive it from the other axioms in this set. So it doesn't have to have get-get equation as one of the axioms. And that's one interpretation of the Boolean location. And here is another interpretation of Boolean locations. Like I said, these operations, they are left abstract. So maybe you want to try to come up with different interpretations for them for different purposes. So for this particular one, what we are doing is we are trying to lock down all the states that we have seen, that we have put basically in the evaluation of the program. So in this case, this monad says that I will interpret x as, well, again, a function that takes a Boolean value. But in this case, I don't return a tuple. I still return a tuple, which includes the original value, but also the second element now becomes a list of bool. So on the previous slide, we have only a single bool that always returns the current value stored in the memory location. But in this case, let's return a list of bool because we want to keep track of all the states that we have put into the memory location array. Then here are the interpretations for the constants and the operations. And you can see the interpretations are different. So when C is a constant, well, we again construct a function that takes the current memory, take the current Boolean value stored in the memory, and then we return a tuple where the second element